Okay, so we got some big news in the neurotech space. Researchers at the University of California, San Francisco were able to decode full words and sentences from brain signals using 128 electrodes placed over their participant's brain, allowing him to speak. Hey, I'm Harrison Canning of the BCI guys, and wow, do I have some incredible news to share with you. On Wednesday, July 14th, I was cooking fish. Okay, that's not the news. And while I was cooking fish, I heard on NPR that researchers had developed a new speech neuroprosthetic device capable of turning brain signals directly into text. Their device, which was placed over the motor areas associated with speech, could decipher between words in a predetermined set and construct sentences with them. So how does this actually work? In previous videos, we've shown how brain-computer interfaces can be used to move a cursor around on a screen, and how imagined handwriting can translate to digital letters, and how focused visual signals can aid in slow, non-invasive typing. These are all amazing in their own right, but share one characteristic that makes them slow. They type one letter at a time. In our previous news video, we talked about how researchers at the Howard Hughes Medical Center had improved upon this model to allow a disabled person to handwrite without using his arms. This time, researchers targeted the motor areas responsible for controlling the muscles needed for speech production. Instead of the user having to focus on a secondary action, such as moving a cursor, handwriting, or looking at targets, the user could just speak, engaging different neural signatures for each word, which are then picked up by the implant. The study participant, nicknamed Bravo1, has been unable to speak as a result of a trauma-induced stroke 15 years ago. When Bravo1 attempts to speak, only unintelligible vocalizations can be heard, but his brain responds similarly to able-bodied individuals despite these areas being dormant for so long. The electrode grid picked up this activity and sent it to the computer for decoding in real time. The computer would then decide, using probabilities, which of the 50 predetermined words Bravo1 was trying to communicate, and then display it on the screen. Let's walk through, step by step, how this device actually works. First, Bravo1 is presented with an example sentence for which he is to generate a response. In this case, how are you today? In the next phase, the cortical signals are collected. In this case, the data is collected from an electrocorticography array, or ECOG for short. ECOGs are semi-invasive, paper-thin circular electrodes. They're considered semi-invasive because they are placed underneath the skull but on top of the brain, not penetrating neural tissue. This particular ECOG grid was placed over Bravo1's primary motor cortex, located here. Over on the right, you can see a diagram that shows which parts of the motor cortex controls which muscles. This is called your motor homunculus. The electrode grid is placed directly over the areas that control muscles in the face, tongue, and larynx, in other words, the speech muscles. The brainwave data is then processed and cleaned in order to remove any artifacts or other bad data that isn't needed. Next, the machine has to determine when Bravo1 is trying to speak. As validated by previous research, speech production is associated with activity in high gamma band between 70 and 150 Hz, in the more dorsal areas of the motor cortex that control the face. Once the signal indicates that Bravo1 is attempting to speak, a sample from 1 to 3 seconds after the speech attempt is captured and sent to the deep learning algorithm. Here's a little more about how this works. Each word represents a specific neural signature, which you can see represented on the ECOG strip. During training, a participant is asked to say the target word through multiple trials. Each time, the computer analyzes the neural signature generated from the word and compares it to previous signatures for that word. It then creates a range of acceptable values that correlate with the word. When Bravo1 tries to speak, the algorithm looks for the best match between the signature generated in real time and the signatures in the database. The algorithm then assigns probabilities, like this word has a 60% chance of being dog and a 40% chance of being good. This process yielded about 47% accuracy, which is really good when you remember that we're selecting from a database of 50 words here. Still, 50% isn't all that usable in a real-world setting, so researchers passed the decoded words through a natural language model called Viterbi to determine whether the word meets the context of the sentence. This is similar to predictive text on your phone. Language modeling is typically used for analyzing large bodies of text to provide predictions for which word may come next in a sentence. The researchers used the results from classifications made by their deep learning algorithm in conjunction with the Viterbi decoding algorithm and a language modeling technique in order to more accurately predict which word the patient was attempting to speak. This new model resulted in much higher accuracy rates, averaging from 75%, with the best attempt having a 93% accuracy. Once the algorithm has determined what word Bravo 1 is thinking of, it will display it on the screen. The training occurred over 81 weeks and 22 hours of neural data was recorded. The researchers found that the more data they were able to collect, the more accurate their prediction models were. This makes sense. They didn't notice any significant degradation of quality over time. The results are nothing short of astounding and a sign of hope for those in locked-in states who are unable to communicate. But it still has a long way to go. Adding more words exponentially increases its complexity. It is also important to note that this isn't actually reading your mind. This model relies on the motor area of the brain in order to classify the words by the participant. Basically, the system needs the user to attempt to speak a word in order to guess the word, so it wouldn't work if the user was just imagining a sentence in their head. It needs the user to attempt to speak the words in order for this to work. This is an important distinction made from mind reading, because motor tasks are almost always voluntary. Wow, the future is coming fast. Thanks for watching. Like and subscribe for more neurotech content. Get cool merch like this mug and support us on Patreon at bciguys.com/support. See you in the next video. BCI guys out. Oh God. Basically, what is going on outside? Shut up. Perfect. Wow, the future is coming fast. Thanks for watching. Like and subscribe for more Damn it! Damn it! Ugh. Wow, the future is coming fast. Thanks. That was your fault that time. Wow, the future is coming fast. Thanks for watching. Like and subscribe for more neurotech content. Get cool merch like a shirt or a mug at bciguys.com/support, where you can also support us on Patreon. Thank you. See you in the next video. That might be the ending.